If you've seen the video on the previous slide, you might have noticed that it shows a lot of rain, but the whole picture is upside down. What I'm going to talk about is how the world has gone upside down for statistics. So what I'm going to talk about is statistics against AI and ML. 3 decades ago, artificial neural network was seen as a toy. Statistical analysis carried a century-old tradition and prestige and seriousness. Nobody really took the ANN tradition seriously at all. Whereas what happened in the intervening 30-year period is that there has been a huge data explosion and huge explosion in computing power. Of course, all of that is driven through a background explosion we call the internet. The upshot of all of that is that data science, as we call it today, is slowly but surely replacing statistical methods, statistical way of thinking, above all, money that is coming to statistical research. And they are all being channeled to data science. Why? That's where most of the money-making opportunities are happening today. Indulge with me, if you will. If we go back to 1993, we saw the first set of developments of PC implementation of artificial neural network. Before that, artificial neural network has been there, but it has been a game for big mainframe computers. PCs were not in the horizon for ANN modeling at all. But the first set of ANN models for PC started coming out. They were typically primitive models with one hidden layer. I'll talk more about the hidden layer, what happens when you have more than one hidden layer in a different lecture. But they were, even then, even with one hidden layer, they were very, very slow. A model run with 1,000 data points would often take overnight, sometimes 2 days. And then at some point in time, if there is some power glitch, then the whole thing will go off and then you will have to start all over again. I've been there, I've done it. And at the end, what you would get is an output that would produce a suboptimal solution. When you look at it, the solutions are not converging, and then you know you have a suboptimal solution. Back then, statistical model ruled. To give you an idea how much it ruled, here's a quote from Derek Powell and Martin Duffy from SAS Institute. They said very disparagingly to the ANN, artificial neural networks, neurons everywhere and not a brain in sight. Let me fast forward 30 years, 2023. Here's an example of how far this kind of neural network models have penetrated various other disciplines, in this case, economics. So we have had modeling of nightlight economics, which meant basically you look at the night images to predict the level of GDP in a given country. So for countries that have had no published data to speak of, or where you suspect the published data is not telling the truth, you can use satellite image, nighttime satellite image, and see how much the night lights that shows up can actually be used to predict economic growth. Actually, it was used for measuring the level of GDP, not the growth of GDP per se. For example, there is a famous model which contrasts between North and South Korea and uses that to generate a nightlight model to predict what the GDP growth or GDP level in North Korea is in relation to South Korea. And the indirect evidence shows that they are pretty much on the ballpark. Now, what happens with that kind of model is that when you have very, very granular data, that model does not work very well. So if you have, for example, high resolution, but at a more local scale, let's say 5 kilometer by 5 kilometer, and try to predict what happens in that kind of population or economic development, it breaks down. Partly because the nightlight only gives you certain images, but it saturates very, very quickly. As a result, the models are not very good. Here is what happened in 2023. A paper has just been published in the American Economic Review. What it does, it looks at a very granular level resolution of the United States, but not of nightlight, but satellite images during daytime that NASA produces at a very granular level for the United States. And then it uses that artificial neural network model, a convolutional neural network model to be specific, and predicts the growth of population and the growth of GDP 5 years out. And the results are astonishingly good. However, keep in mind, these models we do not really know what goes under that picture. All we have is a very high resolution pixel by pixel surface, and that's it. And that predicts 5 years out GDP growth. So in a different sense, we really do not know how it's doing that. There is no theory behind it. There is nothing behind it at all other than those pictures. And that, having published in a premier journal in economics today, tells us where this thing is going in the future. Where is it going? The future is for the data scientists. To appreciate how far we have come, I have several slides that reiterates what Warren Searle of the SAS Institute had said. This is 30 years ago, circa 1993. He says, the main drawback of using a neural network is that while it can give excellent prediction, it is not a formal modeling process. This means that while a model is created, it's not built to increase understanding of the system. Rather, it has the purpose of extracting patterns and trends from the data and using this either to interpolate or extrapolate values. Executive summary: AI is for prediction, not for understanding what the underlying data generating process is. Then Warren Searle goes on to expand. He said, neural networks are therefore complementary to statistical model building, and as such should be seen as another tool in data analysis and not, and he puts it in bold, he underlines it and says, not a replacement for formal modeling process. Again, the executive summary is exactly the same in my previous slide. Searle then goes on to give us a helpful translation, if you will, between statistical terminology and machine learning terminology as we use it today. So for example, it said that when you look at independent variables as a statistical terminology, here we use them for machine learning, artificial intelligence, calling them inputs. Similarly, predicted values here are called outputs, and so on and so forth. He also notes that there are some terms that are used in machine learning are contradictory to what we use them in statistics. For example, the term bias has a very specific meaning in statistics, but the way machine learning terminology is used is simply an intercept in a regression, for example. Other terms are similar. For example, we use forecasting. Here it's used as prediction. Then Searle also gives a sort of a translation from what terminology we use for statistical purposes versus what we use for machine learning. For example, Cohen network, which was very big back then, Cohen self-organizing maps, for example, they are basically discrete approximations to principal curves and surfaces. And those kinds of network was used for things that at that time was not possible in statistical analysis for one simple reason. If you had huge quantities of data, then your statistical methods or statistical canned packages were pretty much useless. That brings us to the question, what are the fundamental differences in how we model in economics or statistics? They're pretty much in line with one another. What we typically do is we put a lot of emphasis on theory before we build any model to predict. So first, there's a lot of discussion that goes on into theory building, and then after that, once we are sure that the theory is sound, then we go on to use the theory to actually model and predict the future. Whereas in the ANN, ML, AI literature, the entire focus is on prediction. So this reminds us of what Deng Xiaoping, the Chinese supreme leader, once said: black cat or white cat, if it can catch mice, it's a good cat. So in that sense, ML AI is a good cat. So having modeling with these kinds of ends is very different way of thinking than what we had done before. So for example, some of the AI models have more parameters than input data. If you think about that from a statistical modeling point of view, that's absolutely unthinkable. We would not in a million years think about modeling something where you have very few data and then you add parameters to the model which is bigger than your data set. That's just absolute no-no. Why? Mainly because the error term becomes very, very large, and therefore your models become very unreliable. Here, that's not necessarily so. As we will see when we talk more about the AI models, that this is quite common. However, we really do not understand why that gives us decent prediction. And that also raises a suspicion whether what we think are good predictions may not actually be so, because the underlying structure may not be robust at all. Again, we do not have any answer to that question yet, and I'm not even sure whether any AI model will be able to answer that question ever.